Nah, hey, should we get behind something?
Hi everyone! In the previous video we derived the rocket equation in one dimension. In this video I want to talk about the rocket equation in two dimensions. This will allow us to compute more interesting things, like how to actually reach orbit using a gravity turn. Okay, let's get to it. So here's a rocket at some point in space. We could just use the Cartesian coordinate system, but that's kind of boring. It's more interesting to write down the equations in the polar coordinates. This point here represents the center of the Earth, so obviously this is not in scale. So what is the set of rocket equations for velocities in the r and theta directions? First, let's write down what the acceleration of r and theta is in these coordinates. We could do this the quick way, or we could do it the interesting way, using what we know from general relativity. Well, since this channel is primarily about general relativity, we'll do it the second way. It will be a good opportunity to review some basics of intrinsic geometry. Alright, so we know that the motion in the absence of forces is given by the geodesic equation. The indices I label the components of arbitrary spatial coordinates. In our case, they are r and theta. For those of you who are new to this channel, or general relativity, you should know that repeated indices imply summation. This is the so-called Einstein summation convention. The Christoffel symbol can be easily computed from the metric and its inverse. I put links in the description box to my earlier videos on this stuff if you need to refresh your memory, or perhaps if you're new to this subject. So the geodesic equation for the r and theta components are... So these are the accelerations along r and theta. However, we have to remember that these components are in the basis e sub r and e sub theta, which are not in general unit vectors. But we can express them as unit vectors using their relationship to the metric, which is this. This gives us an extra r here. There's one more thing we have to do. V superscript r is r dot, the velocity along the r direction. But V superscript theta is theta dot, the angular velocity. Which is fine, but it's better to work with quantities that have the same dimensions. What we want is the velocity along the theta direction, which is r times theta dot. Let's denote that by v prime. If we take a time derivative of v prime, we get this. Let's bring this equation down here. These two terms are the same as these two terms, so we can write v prime plus r dot theta dot. So in terms of v prime, we have we should also write this term in terms of v theta prime. There. Now we can drop the primes. So we have our two-dimensional equations of motion for an object with no forces acting on it. Let's now add some forces to get our rocket equation. T is the force of the thrust, which we'll talk about in a minute. F is the force of friction, or air resistance, and G is the gravitational acceleration. Let's move these terms to the other side. So now we want to choose what kind of thrust function we want. The most efficient way to use fuel is to align the thrust with the velocity. In other words, all the fuel is spent on giving the rocket speed and none is wasted on changing the rocket's direction. Now in reality this cannot be achieved 100% because if the rocket starts out vertically and you don't tilt it, you will just go straight up. So what's usually done is that a few seconds after the rocket takes off, the engines tilt a little bit, usually no more than a few degrees. This maneuver is called pitchover. It only lasts a few seconds, typically, but it's enough to tilt the rocket's trajectory so that gravity can continue the tilt. So after the pitchover, which only uses up fuel for a few seconds, the gravity takes over and turns the rocket into a curved trajectory. This whole maneuver is called gravity turn. Okay, so we want the thrust vector to be this. T0 is the thrust magnitude. It's equal to the exhaust velocity times the mass flow rate. R is a rotation matrix that tilts the thrust by an angle gamma. T1 is the time at which the pitchover maneuver starts. So until then, the thrust is fully in the R direction. After T1 and until T2, the thrust is tilted by angle gamma. And after T2, the thrust is in velocity direction. V here is the speed. For the friction term, I'm using the standard expression that depends on the speed squared and the velocity direction. Now we just have to add the equation for R to have a complete set of equations for the rocket's trajectory. Okay, let's plug in some numbers and try to send the rocket into orbit. I'm using numbers for the Saturn V rocket, which I found to be these. For the T1 and T2, I chose 10 and 12 seconds respectively, and for the pitchover angle gamma, I chose 0.069 degrees, a very small angle. So the engines only have to be diverted for 2 seconds at 0.069 degrees. Okay, let's plug these numbers into ND-solve in Mathematica, and we get... So this is one simulation up to 3 different times. TF is the time it takes the rocket to use up all its fuel. That's given by m0 minus m dry divided by k. This black line is the trajectory of the rocket. It reaches a height of about 58 kilometers before it runs out of fuel. The second picture shows the trajectory up to about 94 minutes after takeoff, which is about the time it takes to complete one orbit. Its height at that time is about 500 kilometers. And finally, the third picture shows that trajectory up to about 122 minutes. Here we see that the rocket is moving too fast. It's leaving the orbit. In real life, the rocket doesn't follow a perfectly predetermined path. Instead, the thrust is continuously adjusted. There's a target trajectory, but small deviations are inevitable, so the system constantly corrects to stay on course. So that concludes this video. I hope you had as much fun watching it as I had making it. Until then, cheers.
Booster ignition and liftoff. The crew of Artemis II now bound for the moon. Humanity's next great voyage begins.
Good roll pitch.
Roger, roll pitch.
Houston, now controlling the flight of integrity on the Artemis II mission around the moon.
The integrity